This is part 10 of the series Integration, and in this part we're going to start looking at the second part of the fundamental theorem of calculus, or the second fundamental theorem of calculus. Now, before we actually get into the second fundamental theorem, I want to recap something that we've already talked about. Let's look at definite integral as a number, and that's what happens when we use the first fundamental theorem of calculus, or FTC1, to take a definite integral. The integral from 0 to pi over 2 of cos x dx is, we take the antiderivative of cosine, which is sine x, and we evaluate that at pi over 2, which is sine x of pi over 2, minus sine x evaluated at 0. So sine of pi over 2 is 1, sine of 0 is 0, so that equals 1. So the definite integral as a number is the way we've been using the first fundamental theorem of calculus. Now, let's take a look at a second scenario. Let's say that we had to evaluate a function at several values of our upper limit of integration. Now, for this function, it wouldn't really be too bad because cosine is an easy function to take the antiderivative of. But if you had a more involved function, it would be rather tedious to have to repeat this integral if you had to do this over, say, 4 or 5 separate values. It would be much more convenient if we could set a variable for our upper limit of integration, and then we'd only have to evaluate the antiderivative at those different values. So we'd take the antiderivative once and then evaluate at those different values. Well, that's in fact what we can do. We can revisit this function, and let's use x as our upper limit of integration. So to do this, we would say the definite integral from 0 to x of cosine of t. Now, it's important to note that we're not using an x here because the definite integral is not a function of this t value. So this value doesn't have to match. And we're using a separate value. You could use anything you want in here, but it's traditional to use a t so that you don't get confused between the x, which is the variable of our upper limit, and the variable of integration. So we take the antiderivative of cosine, which is sine t, and we evaluate it from 0 to x. And so evaluating first at x, t equals x, so that becomes sine x, minus sine of the lower limit, which is sine 0. In this case, the lower limit drives our sine function to 0, so we have sine x minus 0. So conveniently, this comes out to sine x. Now you'll notice that a very important thing happens here, that this result of our definite integral is in fact a function. It's not a number. And that function, if we were to take the derivative of that function, we would actually get our integrand of our original expression, with the only difference being the variables have changed. And that rule is summarized in what's known as the second fundamental theorem of calculus. If f is continuous on an open interval I containing some value a, then for every x in I, the derivative of the definite integral from a to x of some function f of t dt is equal to the function evaluated at that upper limit. And what this is saying, quite simply, is that the definite integration process is the inverse of differentiation. And that's one of the reasons why this is one of the primary theorems that we deal with in all of calculus. That integration, definite integration, and differentiation are inverse operations. So let's take a look and see how this works in practice. So in this example, we are to take the derivative of the definite integral from 0 to x of the square root of t squared plus 1 dt. Now, when applying the second fundamental theorem, the first thing we have to be concerned about is this function continuous on its interval? And we know that yes, it is. This function is continuous from 0 on, so it is integrable, so we will be able to do this operation. Your first impulse then might be to try and take the antiderivative of this piece, and you would quickly find out that we haven't yet learned those techniques to allow you to do that, and fortunately that's not necessary. That's all we have to do is apply the second fundamental theorem, which simply tells us the derivative of the definite integral is the integrand replaced with the upper limit of integration. So the result here is simply square root of x squared plus 1. And that's our final result. I know it sounds too simple to be true, but it is. That's one of the beauties of the second fundamental theorem. Now, with more complex expressions of x, this gets slightly more complicated, but it's still a relatively straightforward concept. So let's try another example and see how it works. In this example, we want to take the derivative of the integral from pi over 2 to x cubed cos t dt. Now, again, we have a continuous function, so this operation applies, and we can apply the second fundamental theorem. But here we have a little complication. We don't just have an x term, we have an expression in terms of x. And so what we're going to have to do is we're going to have to apply the chain rule to this situation. Now, if you recall from the chain rule, if we had some function like this, we could say that we had a substitution going on where we said u was x squared plus 1, and then we could rewrite the function y as the square root of u. So when we took the derivative, we'd be doing a derivative of y with respect to u, and then taking the derivative of u with respect to x. And that was the chain rule. So that's what we're going to do in this case. In this case, we're going to set our u to equal x to the third. And so what we're going to have is we're going to have the derivative of f with respect to u, and then we're going to have to take the derivative of u with respect to x. So that's in essence what we're going to do. And what it boils down to is nothing more than saying, well, using the fundamental theorem of calculus, we'd have cosine of u times the derivative of u, which is 3x squared. Go ahead and back substitute now, and we have cosine of x to the third times 3x squared, which, simplifying that, becomes 3x squared cos x to the third. So to recap this, that's all we did was take the standard second fundamental theorem and just substitute our upper limit, which in this case was our u, and then take the derivative of our upper limit. And that becomes our final result for the second fundamental theorem. Let's continue our lesson in the next section. In this section, we're going to look at a new theorem called the net change theorem. And before we get into the net change theorem, I want to do a quick recap in our fundamental theorem, which states that the integral from a to b of f of x dx is equal to the antiderivative of f evaluated at b minus the antiderivative of f evaluated at a. We also know from the definition of an antiderivative that the derivative of an antiderivative is equal to the original function. So we can replace this expression with this and say that the integral from a to b of this rate of change with respect to x is equal to the antiderivative of that function evaluated at b minus the antiderivative evaluated at A. And this brings us to the net change theorem, which says the definite integral of a rate of change of a quantity gives the total change or net change in the quantity on the interval A to B. So if, for example, we were plotting on an XY coordinate plane distance versus time, this function would be a velocity function because it's a rate of change, distance per unit time. And if we have some interval from A to B and we integrate this function across this interval, we integrate this rate of change, this net change theorem tells us that we're going to be accumulating this quantity. We're going to be accumulating distance across this interval. So the integral, the definite integral of a rate of change gives us a quantity across which we are integrating. So this is going to be a very valuable technique we're going to use in the very near future. So let's take a look at an example and see how this is applied. In this example, we're given that a chemical flows into a storage tank at a rate of 180 plus 3t liters per minute, where t is between 0 and 60. Find the amount of chemical that flows into the tank during the first 20 minutes. So this is an application of the net change theorem. So because we're looking for the amount of a quantity, we're going to be integrating across some rate of change. And the rate of change is the rate of change of the amount of chemical in the tank per unit time. So we're going to take a definite integral, and our interval is from 0 to 20 because it says the first 20 minutes. So our lower limit is 0, our upper limit is 20. Our function is 180 plus 3t, and our variable of integration is t, so it's with respect to time. So we would go ahead and evaluate this, and we have 180t plus 3t squared over 2 evaluated from 0 to 20. So 180 times 20 is 3600, and 20 squared times 3 divided by 2 is 600. And when we put 0 in here, that's minus 0. So this gives us a total of 4,200 liters in the first 20 minutes. So you can see that the antiderivative of this rate of change gave us a quantity of chemical in the tank. In the next section, we're going to look further into the net change theorem as it applies to a very common application in terms of particle motion, linear motion of particles. So let's go ahead and go on to the next section to see what we can uncover there.